In this study, we present an integrated current and vibration sensing system designed to monitor drone docking station conditions using machine learning models for anomaly detection. The system also offers a plug-and-play monitoring capability with the potential to be adapted to various machinery. We utilize a centralized multi-channel current sensor to monitor 8-stepper motor channels and distributed vibration modules using 3-axis accelerometers on critical moving parts. To ensure data integrity, we implemented a decentralized logging architecture using micro-ROS on ESP32 controllers, allowing for Wi-Fi time synchronization across all modules. For anomaly detection, we compared two distinct approaches. Model A is a supervised LSTM-based classifier trained on labeled data to identify known faults. Model B is an unsupervised CNN-based autoencoder. By training solely on normal operation data, Model B detects anomalies by measuring reconstruction residuals. We use short-time Fourier transform to extract optimal time-frequency features for both models. We validated the system on a real-world Horus box across 3 phases: releasing pushers, X-axis alignment, and Y-axis alignment. Both models performed exceptionally well. While the classifier achieved near-perfect accuracy, our unsupervised reconstruction model reached over 98.99% accuracy and a 98% F1 score. Since the performance difference was not statistically significant, we recommend their reconstruction model for real-world use because it requires no expensive labeled data. We also verified model stability by adding Gaussian noise. The system maintained over 80% accuracy even at high noise levels, particularly in phases 1 and 3. In conclusion, we have developed a robust, non-invasive device for docking station health monitoring.